I think we've got the recording going now, so I want to welcome everybody to another Earthly class. And we're very pleased to welcome back Michael Previdi. Today's program is about Arctic amplification. What is it? Why does it happen, and why does it matter? So a brief introduction. Michael earned degrees at Rutgers University, and he's currently Lamont Associate Research Scientist. His research focuses on the ocean's atmosphere and their interactions. He's explored the North Atlantic Oscillation and air-sea exchange of carbon dioxide. He also looks at the global hydrological cycle and anthropogenic forcings. Briefly, the Arctic amplification refers to a phenomenon in the higher latitudes involving faster warming in the higher latitudes than in lower latitudes due to climate change. One of the more obvious signs of climate change, in part because of its magnitude and acceleration since 1990. The Arctic regions are warming at about twice the rate of average global surface temperatures because of positive feedback mechanisms. I know many of you are familiar with feedback mechanisms, but just want to explain it briefly in case anyone isn't. In a feedback mechanism, a positive feedback mechanism, such as shown here, if there's more warming to start at that spot, means more ice melts and the amount of sunlight reflected back to space, the albedo, decreases because more energy is absorbed on the Earth's surface and in darker seawater than the ice. And if more energy is absorbed, that leads to more warming, and the whole cycle continues. So we have a positive feedback involved in the Arctic amplification. Related to the Arctic amplification are a couple of other phenomena. One is called the Arctic oscillation, also called the Northern Hemisphere Annular Mode, or NAM. And there's an equivalent Southern Oscillation, or Southern Annular Mode, SAM. These involve changes in sea level pressure over time, but there's no established periodicity. There seems to be some connection with weather patterns caused by the Arctic oscillation, but exactly what these are is still unclear under active investigation. Arctic oscillation is somewhat related to what happens with the polar vortex that many of us have heard about in the last few years. We have two basic states: stable polar vortex, where the jet stream confines low around the pole, and the wavy polar vortex, which has more of an effect as it passes over North America and Europe, bringing warm air northward and cold air southward at different times. Related to this is something called the North Atlantic Oscillation, better studied weather phenomenon involving fluctuations of the sea level atmospheric pressure between the Icelandic low and Azores high. These patterns control the direction and strength of westerly winds and storm tracks across the North Atlantic. One of the very first Earthly class programs back in 2000 featured Dr. Martin Visbeck and his research about the North Atlantic Oscillation. Unfortunately, due to changes in technology since then, few of the resources that were created for that program remain available. Michael has done two previous Earth class presentations, most recently in 2015 on global climate models. North Atlantic Oscillation has been known since the 19th century. It's somewhat similar to the ENSO, Pacific El Nino Southern Oscillation. But the North Atlantic Oscillation mainly involves the atmosphere, not air-sea interactions. There's also something called the Atlantic Multiple Daily Oscillation, which is another pattern of atmospheric and sea surface temperature variations that can influence rainfall patterns, hurricanes, and fish populations. So now it's time for Michael to take over and tell us about his current research. Michael, I'm going to stop my share and you can try to start yours.
Okay. Okay, well, I'd like to, first of all, thank Mike for inviting me to come back and do another Earth to Class. As he said, it's been 8 years at this point, so I guess I was due to do another one. Thanks also to everyone who's joined this morning. I don't know how you all usually do this, if you save questions for the end, or if you just, if anybody has a question during the course of the presentation, certainly feel free to, as far as I'm concerned, interrupt me and ask that question or clarification. So as Mike already introduced, today's topic is on Arctic amplification, and I've divided my presentation up into 3 general parts. First of all, I'll just spend a few minutes describing what Arctic amplification is. The second part is to explain some of the physical mechanisms that cause Arctic amplification. And finally, I'll close up the talk by saying a bit about why Arctic amplification matters. So first of all, just a general definition. Mike already defined this in his intro, so probably not necessary, but maybe it's worth repeating. So Arctic amplification refers to the enhancement of near surface air temperature change over the Arctic both relative to lower latitudes and also relative to the global average temperature change. So the Arctic temperature change is larger than both lower latitudes and the global average temperature change. It turns out that Arctic amplification is really a very robust feature of the climate response whenever we perturb the climate. And so I'll show you a few examples of that. First of all, this plot shows observations of surface temperature change for the past few decades, for the period 1979 through 2019. This map would not look much different if you were to add the few years that have happened since 2019. You can see very clearly that most of the world has been warming over the past few decades, as we all know, but some regions have been warming more than others. And I think it's pretty obvious from this figure that the Arctic stands out as a region that has been warming the most over the past few decades. And in his intro presentation, Mike said that the Arctic has been warming at about twice the rate of the global average. That's actually been kind of the number that people have been using for a while now, is that the Arctic warms at twice the rate of the global average. There's actually been a couple of recent papers that were published last year that says over this period that I'm showing here, the Arctic has actually been warming 4 times faster than the global average. So even more enhanced warming over the Arctic in the last few decades. So Arctic amplification is a feature of recently observed climate change. It's also a feature of past climate changes, and this is just one example of that. This is a reconstruction of temperature change, surface air temperature change at the last glacial maximum, which was about 20,000 years before present. This reconstruction was obtained by assimilating or putting paleoclimate proxy data into a global climate model. And what I mean by paleoclimate proxy data, these are environmental indicators of past climate change. And in this particular example, there were a few different indicators of past sea surface temperature changes at the last glacial maximum. And we only have these paleoclimate data over a relatively few number of locations across the globe. So what was done in this exercise to produce this plot was to put those paleoclimate data into a global climate model, and the climate model essentially fills in the rest of the field, fills in the gaps in between where we have data. And so you can see here that unlike the past, few decades where the world has been warming, if we go back to the last glacial period, of course, the world was colder than it is today. And you can see that, where is that cooling the greatest? Well, it tends to be the greatest in the polar regions. So you see both over the Arctic and the Antarctic, there's an amplification of temperature change. And so this works in both directions. Arctic amplification works in both directions. It works when the world is getting warmer. It also works when the world is getting colder.
Mike, could you give some examples of the paleoclimate proxies that might be used?
Sure. In this study, there were a few different types of geochemical proxies that were used. The ones that were used the most were magnesium-calcium ratio, the magnesium-calcium ratio, and also oxygen isotope ratios. And so the way that these are measured is, there are sediment cores on the ocean bottom, and these sediments trap the remains of calcifying organisms, marine organisms, and these magnesium-calcium ratios, oxygen isotope ratios are recorded in the shells of these calcifying organisms. And so by measuring those ratios are related to the sea surface temperature where the organisms live. So that's how we can estimate past temperature changes.
Thank you.
Sure. So those are two examples of Arctic amplification in recently observed climate change, and also it's a robust feature of past climate changes. I'm showing here as just one example of that, the last glacial maximum temperature change, but there are a number of other past climate changes that we have evidence for Arctic amplification. Finally, that's past and present. What about the future? Well, it turns out that Arctic amplification is also a very robust feature of projected future climate change from climate models. And this is one example of that. This is showing a projection of temperature change between the periods 1985 to 2014, so essentially representing the present day climate, and the end of the 21st century, the period 2070 to 2099. This is an average of several different climate models that participated in CMIP6. CMIP6 is the latest generation of global climate models that are being used by the climate community. And this particular projection is based on a scenario of so-called business as usual greenhouse gas emissions. So, we continue to pump greenhouse gases into the atmosphere at the rate that we have been for some time now. And the models tell us, if we continue to do that, what will happen to the climate at the end of the century. And again, you can see very clearly, I think, that so the world warms, everywhere, but the Arctic warms quite a bit more than the rest of the globe. So again, this is really a very, very robust response of the climate system when we perturb it, this phenomenon of Arctic amplification.
I could just pop in again for a moment. You'll see the
Sure.
source here is listed as NOAA's climate change web portal. And on the Earth to Class website for this program, you'll find a link to some activities from the climate change web portal.
Yes, and so that's why I've highlighted that in red. That's where I was going next with this. So I wanted to spend a couple of minutes just describing what NOAA's climate change web portal is. And then I have, as Mike said, there's a set of instructions on the Earth to Class website that tell you how to generate a few simple plots using this web portal. So after I spend a couple minutes introducing this, I would like to maybe just take like a 5-minute break where you all try to generate these plots using the instructions that were provided. And then we'll resume and we'll discuss the plots. Has anybody, just out of curiosity, has anybody actually used this climate change web portal before? Anybody in the audience?
I don't count.
Okay, so I don't hear anyone else speak up, so I assume that nobody has used it. So this is a web portal that was designed by NOAA, and it provides an easy way to visualize output from the latest generation of global climate models, the CMIP6 climate models. And that plot that I showed in the previous slide, as I indicated, was produced using this web portal. So the point of this little exercise I wanted to do today was just to produce a couple of simple plots of climate model output that will help us to better understand a few key aspects of Arctic amplification. So with that, let me just exit the PowerPoint for a minute. And actually, I did not bring up, I should have brought up this link. So let me go to the climate change web portal. And so this is what it looks like. There's some default plot that's a series of plots that's shown when you go to the link that I provided. So you can do various things with this web portal. So there's this series of drop-down menus on the left here where you can select various options. So first of all, experiments. So these are various greenhouse gas emission scenarios for the future, for the 21st century. They go from kind of a climate change mitigation scenario. So a scenario that assumes that greenhouse gas emissions peak over the next few decades and then start to decline for the rest of the century. So it goes from that end of the spectrum to SSP5 8.5, which is what we'll use for this exercise. And that's, again, kind of a business as usual greenhouse gas emission scenario where we just continue to increase greenhouse gases into the atmosphere as we have been. So let's select that. You have the option of plotting a number of different fields. So if you select, and those fields can be plotted as just as shading or as contours. And so in this example here, you can see that we have temperature, near surface air temperature, that's plotted as shading and overlaid with contours. So you have the option to plot it in either way. So the variables that can be plotted, there's a number of atmospheric variables. We're going to focus today just on air temperature, which is the near surface air temperature, but there's a number of others. There's precipitation and winds. There's a number of ocean variables that you can plot: sea surface temperature, salinity, sea ice, and so forth. So there's ocean physical variables, and there's also ocean biogeochemical variables such as primary productivity and surface ocean pH and so forth. So I'm just going to select air temperature since that's what we'll focus on today. Models. So the default option here is to just plot an average, a multi-model average of several different CMIP6 models. So for the exercise today, that's what we're going to do, is just plot the multi-model average. But if you wanted to, there's a number of individual models here, CMIP6 models that you could choose to select and just plot the results from individual models. Statistic, we're going to focus today on just the anomaly. So the anomaly is just a change in climate relative to some reference period. So in this exercise that we work through, we'll choose a reference period that's representative of the present day. And then we'll look at the changes relative to that reference period or the anomaly at the end of the 21st century. There's a few different variations on that you can look at if you choose to. We won't do that today, but if you have an interest, you can look at those as well. And if you click on the little question mark here, there's some information about those other statistics that you can examine. And I'll note that in this plot that's shown here as an example, and also in the exercise that we do today, we'll focus really on this plot in the top right here, which is the anomaly. So it's the climate change between your reference period and your end of century period. So there's a few other options here. If we scroll down the page, you can plot your climate change averaged over the entire year, and you can also plot for individual seasons of the year. And so the first part of the exercise that we'll do today the point of that is to see how Arctic amplification varies depending on what season you look at. So we'll create a plot for each of these 4 seasons here. Next, historical period. That's the reference period. That's the reference period that I just referred to. First of all, I'm just going to select January, February, March. And so the reference period, or the historical period, that's the period that your anomalies are relative to. So what I'm going to do here is just select the most recent reference period. So the period 1985 through 2014. Next is the 21st century period. So that's the period later this century that we calculate the climate change at. And so I'm going to select the last period here, the end of the century, 2070 to 2099. Finally, last couple of options here. We'll focus first on the first part of the exercise at just looking at a global plot. So something that looks like this example here, where the climate change is plotted everywhere across the globe. But you also have the option to select individual regions here. So for the second part of the exercise, we'll actually select the Arctic and just create a plot just over the Arctic. Finally, you have the option to customize your plot by defining contour intervals and changing the color scale if you wish to. So that's just a short introduction. And I'll say that once you make your selections on the left here, you can generate the plot by hitting Make Slideshow here. And so that'll generate a new plot based on the specifications that you've provided on the left. So with that, does anybody have any questions on that short intro to the NOAA Climate Change web portal? Okay, so maybe let's take like just 5 minutes, and for those who want to, you can take a look at those instructions that were provided on the website, and try to generate the few plots that are requested in those instructions. And after 5 minutes or so, maybe we can discuss what you found.
Yeah, I'm going to stop the recording while we do this.
Okay. Okay, so was everybody able to get those plots to work? Does anybody want to volunteer to address the first part? When you looked at the different seasons, were there any seasons where you did not clearly see Arctic amplification occurring? If nobody wants to chime in, I can go to my slide that I produced. So this is what this is the series of plots that that you should have gotten if it worked out for you. And so these are the 4 seasons of the year, and you can see, I think, in 3 of these 4 seasons, so winter, spring, and fall, it's pretty clear that there's Arctic amplification occurring, right? You know, you see the Arctic is warming, faster than the rest of the globe. The exception to this is really the summer season. So in the summer, which is shown here in the lower left, there's of course still warming over the Arctic, but that warming isn't necessarily greater than lower latitudes. So much of the Arctic Ocean here, for example, actually warms a little bit less than parts of the lower latitudes, such as the continental U.S. and various parts of Europe and Asia, Northern Africa. So the point of that first little exercise was to really illustrate that Arctic amplification really is a cold season phenomenon. It doesn't occur in the summertime. And this next plot, this illustrates the same thing. This is a figure from a paper of mine that was published a couple of years back. And what's shown here is surface air temperature change. So the first 2 plots here, the top 2 rows, this is surface air temperature change as we observed over the period 1979 through 2018. The second panel is the same period, but the temperature change as simulated by the previous generation of global climate models, CMIP 5. And finally, the bottom panel here, this is a more idealized experiment from the CMIP-5 climate models where we instantaneously quadrupled the atmospheric CO2 concentration and then allow the climate to respond to that. And so in each case here, we're plotting as a function of latitude the surface air temperature change for the different seasons, which are color-coded as indicated by the legend on the top left, and also for the annual average, which is shown in black. And you can see here as we move from the equator to the pole, to the Arctic, you see that in most seasons of the year and in the annual average, the temperature change gets larger. So we have Arctic amplification occurring. The exception to that, again, is the summertime, JJA, June, July, August, where you see the Arctic actually warms, just like our spatial plots on the previous slide indicated, actually warms a little bit less than lower latitudes. So again, illustrating that Arctic amplification really is a cold season phenomenon. So that was the first part of the talk. What is Arctic amplification? And so now I want to move into the second part of the talk, which is why does it happen? What are the physical mechanisms that cause Arctic amplification? And so this plot here, if you were able to get the second part of the exercise to work, this is the plot that you should have produced. And what this exercise asked you to do was to create a plot just for the Arctic this time, and to plot the surface air temperature change over the course of the 21st century as shading, and to overlay that with contours that show the change in the sea ice area. And so what you can see here pretty clearly, hopefully, is that, so the Arctic warms everywhere, but the maximum warming occurs over the central Arctic, over the Arctic Ocean, and that coincides with where the greatest sea ice loss is occurring. So you see that over the central Arctic Ocean, we have in the multi-model average sea ice losses of greater than 70% over a good part of the Arctic Ocean, and that region of maximum sea ice loss coincides with where we have the greatest warming over the Arctic. And so the point of this figure, and I have a similar figure on the next slide from my same review paper. The point of these figures is to show that again, there's a very strong spatial correspondence between where the Arctic warms the most and where the greatest sea ice loss occurs. So it's an indication, just looking at these plots, that sea ice is pretty important in explaining why Arctic amplification occurs. And so the next question you might have is, well, okay, so sea ice is important. Well, why is sea ice important in causing Arctic amplification? Well, there are a couple of different reasons, and just generally, there are two important effects of sea ice loss that matter for Arctic amplification. So the first of these is sea ice albedo effects, and the second is sea ice insulation effects. So I'll describe what each of those means. Sea ice albedo effects, Mike already gave an introduction to this at the start of our talk today. So just to review, the idea is that if we follow these different steps here that are indicated in the schematic, as the Arctic warms, so step one, as the Arctic warms, ice cover melts, which exposes a less reflective water surface underneath the sea ice. Because that water surface is darker than the sea ice that previously was on top of the water, the open water is able to absorb more of the incoming solar radiation, more of the incoming sunlight. That acts to warm the ocean mix layer, the top part of the ocean, as well as the air that's in contact with the ocean. So that's step two. And then step three in this feedback loop is, once we warm the ocean and the overlying atmosphere, we melt more sea ice and the cycle continues. So as Mike said in his introduction, this is an example of a positive feedback loop. So some initial warming causes ice loss. That ice loss leads to additional warming. So a positive feedback loop acts to enhance the initial warming. So that's the idea behind sea ice albedo effects. That's the first reason why sea ice loss is important for Arctic amplification. The second reason is sea ice insulation effects. And what I mean by that is sea ice, when it's present, acts as a great insulator, which limits the heat exchange between the ocean and the overlying atmosphere. And so in the cold season, so in the fall and the winter, also in the spring, the Arctic atmosphere is much, much colder than the ocean below it. So when sea ice is present, again, it acts as a great insulator. It inhibits the heat transfer from the much warmer ocean to the much colder atmosphere. And you see in the schematic here on the right, when sea ice is present, maybe a typical value of the heat transfer from the ocean to the atmosphere would be about 10 watts per meter squared. When sea ice goes away, though, when it gets thinner and when it becomes less extensive, that heat transfer from the warmer ocean to the much colder atmosphere increases dramatically. So it can increase by up to 2 orders of magnitude, as shown here in the schematic. So we can go from a heat transfer, a heat flux of 10 watts per meter squared from the ocean to the atmosphere to up to 1,000 watts per meter squared. So this is the second the second reason why sea ice loss is important, why it causes Arctic amplification, because when the sea ice melts in the cold season, we lose that insulating capacity of the sea ice, and we have much greater heat transfer from the ocean to the atmosphere, and that warms the lower atmosphere, which is what Arctic amplification is. It's this enhanced warming of the Arctic atmosphere, the lower atmosphere, I should say. And so that leads into my next slide. So when we have the sea ice loss happening, and we're increasing our heat transfer from the ocean to the atmosphere, it turns out that heat that's released into the atmosphere really is trapped in the lowest part of the atmosphere near the surface. And so we say that that there's a so-called bottom heavy warming is a signature of Arctic amplification. And what that means is that the warming really maximizes near the surface. And the reason for that is illustrated in this slide here. So what I'm showing here in this plot, this is an example of vertical temperature profiles over the Arctic. So just how the air temperature varies with height. And this is shown for 6 different stations that are located around the periphery of the Arctic Ocean. These are just illustrative. These temperature profiles are very characteristic of what the temperature profile looks like in the Arctic during the cold season, during the fall, the winter, and the early spring. And what the temperature profile looks like, as you can see here in this picture, it's characterized by what we call a surface-based inversion. And what an inversion means is just an increase with temperature with height. And you can see that in the area that I've circled here. This is the area that's nearest the surface. And as you move up over the lowest couple of kilometers of the atmosphere, the temperature actually gets warmer, which is not the typical situation. Usually as we move up in the atmosphere, it gets colder. But over the Arctic in the cold season, it's actually the opposite. And we have an inversion. The temperature increases as we move up in the atmosphere. And the reason that's important is that this is a very stable atmospheric profile. And what that means is that, since we're in a situation here where the coldest air is near the surface, the coldest air is the densest air. So that tends to inhibit vertical mixing in the lowest part of the atmosphere. What that means is that when this heat is released from the ocean into the atmosphere, that heat again gets trapped near the surface because it's not able to be mixed up into the higher levels of the atmosphere. And so this is another important reason why Arctic amplification occurs, because of this strong stability of the Arctic boundary layer, the Arctic lower atmosphere, that inhibits vertical mixing and keeps the heat that's released from the ocean to the atmosphere trapped near the surface. Again, here's another figure from my review paper that illustrates the same thing. This is showing air temperature changes as a function of latitude on the x-axis and pressure on the y-axis. Pressure is just a proxy for height, because in the atmosphere, pressure decreases with height. So meteorologists often use pressure as a proxy for height. These are the same these three panels here are the same three cases that we looked at in the previous figure. So that the top row is the observed air temperature change between 1979 and 2018. The middle panel is CMIP-5 climate model simulations of the temperature change over that same time period. And again, the bottom panel is this idealized abrupt 4 times CO2 CMIP-5 experiment. In all three cases, though, again, if we look at the Arctic region, we see that the warming is really greatest nearest the surface. So at the highest pressure levels, which coincide with the near surface part of the atmosphere. And again, that's the reason for this is because of this strong stability of the Arctic lower atmosphere that inhibits vertical mixing. So those are, those two factors that I just described, sea ice loss, coupled with the very strong stability of the Arctic lower atmosphere. These are probably the two most important reasons why Arctic amplification happens. There's a tremendous amount of literature that demonstrates that these factors are very important in explaining why Arctic amplification happens. However, there are also a large number of other factors that have been proposed that may additionally contribute to Arctic amplification. I'm just showing here one example of those other factors that have been proposed. I think this is one of the more, one of the factors we have greater confidence is actually important for Arctic amplification, and that is atmospheric moisture transport. And so as the climate warms, atmospheric moisture transport into the Arctic increases. And what that leads to is an enhancement of the greenhouse effect over the Arctic. And that happens both directly, because when we transport moisture into the Arctic, moisture, water vapor is a very powerful greenhouse gas. So if we increase atmospheric water vapor in the Arctic, we strengthen the greenhouse effect. That's the direct response to increased moisture transport. But also, when we increase moisture transport into the Arctic, we tend to increase the cloudiness, the amount of cloudiness over the Arctic, and that further strengthens the greenhouse effect. And both of those impacts tend to lead to additional Arctic warming and sea ice loss, and therefore are likely to contribute to Arctic amplification. This series of plots here that I'm showing in this slide, this is kind of a prominent example of moisture transport into the Arctic, what are referred to as atmospheric rivers. Atmospheric rivers are just filaments of moisture, of high moisture content air flowing throughout the atmosphere. And there's been some evidence, as indicated in this very recent paper, which was only published last month. There's been some evidence that these atmospheric rivers are reaching the Arctic more frequently, and that they're contributing to Arctic warming and sea ice melt. And that's illustrated in this figure here on the bottom. First of all, panel A on the left, this is showing the AR frequency trend. AR is just atmospheric river. So in other words, how has the frequency of atmospheric rivers reaching the Arctic been changing? And this trend is over the period beginning in 1979 up until the present. And you can see here in the map that the green shaded areas are the areas where the trend is positive. So where atmospheric rivers have been happening more frequently over the past few decades. The plot on the right here, panel B, is showing time series of the atmospheric river frequency in a few different observational data sets. These are the different blue colored curves. also showing in red is also shown in red is the time series of sea ice area. And these time series are for this region here that's shown in red. This is the Barents and Kara Sea region of the Arctic. This is a region of the Arctic that's been warming a lot over the last few decades, and where sea ice has been decreasing a lot over the past few decades. And you can see here in this plot in the time series on the right that the atmospheric river frequency has been increasing. You see this positive trend. And at the same time, the sea ice in this region has been decreasing, as I just said. And so again, there's the suggestion that that part of the reason that the sea ice has been melting, and therefore part of the reason that the Arctic has been warming, because the two kind of go hand in hand, is that these atmospheric rivers are reaching the Arctic more frequently and are contributing to an enhancement of the greenhouse effect over the Arctic that leads to warming and to sea ice loss. Okay, so that's before I start to talk about move into the last part of my presentation about why does Arctic amplification matter, does anybody have any questions at this point about the mechanisms, the physical mechanisms that we think are important for AA? Okay, well, if not, then
no.
Okay. So let me move into the final part of my talk, which is just spending a few minutes discussing why Arctic amplification matters. So why does this enhanced warming of the Arctic region matter for human and for natural systems? And there's plenty of examples of why this matters. I'm only going to highlight today a few of the most important reasons I think why it matters. First of all, when we have enhanced Arctic warming, we as we've been discussing, we lose the cryosphere over the Arctic, so we lose the snow and ice over the Arctic, and that's important for a number of reasons. You know, it can lead to damage, you know, and other alteration to infrastructure, as shown in this picture here. This is a picture from somewhere in the Arctic. I don't know exactly where, but what's shown here is the collapse of a roadway that occurred because of the melt of permafrost. So permafrost is the frozen soil, and so as the climate warms, that ice in the soil melts, and it can lead to a lot of damage, you know, to roadways, as shown here, and also to buildings, you know, other infrastructure. The loss of snow and ice can also lead to potentially dangerous conditions for, you know, a number of activities such as hunting and recreation. A second reason that Arctic warming and sea ice loss matters is that it can have large effects potentially on the carbon cycle. And, you know, that's important because the exchanges of both carbon dioxide and CO2 and methane, CH4, between the ocean and the terrestrial biosphere and the atmosphere, you know, those exchanges affect the concentrations of these greenhouse gases in the atmosphere. And so any changes in those fluxes of CO2 and methane between the ocean and the land and the atmosphere could affect greenhouse gas concentrations in the atmosphere, and therefore affect, you know, can be a feedback on climate warming. And so this schematic here is from a recent paper that discusses effects of Arctic warming on the carbon cycle over the Arctic. And what's shown here are a number of important, what we think are important processes in describing this carbon cycle. I'm just going to highlight a few of the most important processes. So there's the expectation that with warming over the Arctic, that there will be increased productivity of vegetation over the Arctic. So there will be a greening of the Arctic. And, you know, in and of itself, that would act to draw down CO2 from the atmosphere, because when we increase the biomass over land, you know, plants accumulate carbon, you know, so we draw down CO2. But, you know, that's only one part of what's going on here. Also, we expect with warming that, you know, respiration from the soil will increase. And so that has the opposite effect. You know, when soil respiration releases CO2 into the atmosphere, so it counters some of the effect of increased vegetation productivity. There's the additional expectation that as the climate warms, wildfires will increase both in frequency and severity. And, we have some observational evidence of this already. And, so that's a potential additional source of carbon that could be released into the atmosphere. I mentioned permafrost on the previous slide. Permafrost is a huge store of carbon. And so permafrost soils are a huge store of carbon. So, when permafrost melts, there's the potential for that carbon to be released into the atmosphere. That's some of what's happening over land, but of course the ocean is also important in the carbon cycle. And as the Arctic Ocean warms and as sea ice melts, that could have effects on, how the exchange, what the exchange of CO2 is between the ocean and the atmosphere. And, what exactly will happen in that regard is somewhat uncertain. With there's the expectation that as sea ice melts, as you have more open water, that would potentially facilitate greater uptake of CO2 by the ocean. But on the other hand, there's other effects that could come into play as well, such as, enhanced freshening of the Arctic Ocean due to, to ice melt and to increased, runoff from rivers into the ocean. So, that has implications for, the exchange of CO2 as well between the ocean and the atmosphere. So again, just a lot of uncertainty with how, how the ocean atmosphere exchange of CO2 will change in the future, but also just how the carbon cycle in general will change over the Arctic with increased warming. A third reason why enhanced Arctic warming matters, well, it matters quite a bit potentially for sea level rise. And this map here is showing the Greenland ice sheet. Indicated here by the red boundary is the extent of the Greenland ice sheet in the year 2008. This is based on satellite measurements. And also shown by the bluer shading here is a projection of what the estimated Greenland ice sheet extent will be a couple hundred years from now in the year 2300. This is based on the assumption of again, a business as usual emission scenario. We continue to pump greenhouse gases into the atmosphere like we have been, and what could happen to the Greenland ice sheet as we continue to do that. And the Greenland ice sheet has already been contributing to global sea level rise over recent decades, and there's the expectation that will continue and that it will even accelerate in the future. And on the lower left here is showing potential contributions of the Greenland ice sheet to global sea level rise at different time horizons into the future. So in 50 years time, it's thought that that melt from the Greenland ice sheet could contribute, an additional 10 centimeters or about 4 inches to global sea level rise. If we go forward in time 80 years, which takes us about to the year 2100, that contribution to sea level rise could be, a few times larger. It could be on the order of a foot, of sea level rise due to Greenland, ice melt alone. Going even further in the future, that contribution becomes potentially even larger. So this is another huge reason why the enhanced warming of the Arctic is important. Another example of why Arctic warming and sea ice loss could be important. Mike also, I think, alluded to this in his intro earlier today. It's thought that there's the potential anyway that the enhanced warming of the Arctic and the associated loss of sea ice could lead to more frequent extreme weather at mid-latitudes of the Northern Hemisphere. And let me spend a couple of minutes describing why it's thought that could be the case. So the jet stream, which you're all familiar with, the source of the energy for the jet stream is the temperature difference between the Arctic and the lower latitudes. And so as that temperature difference decreases, which is what happens as the Arctic warms more than the lower latitudes, the jet stream becomes weaker. And so that's pretty well established, that's well understood. And, that could have a number of implications. A weaker jet stream could have a number of implications. One implication of that is that, the jet stream is what steers the weather systems that affect, our weather at mid latitudes, so the high and low pressure systems that propagate, from west to east, are driven, steered by the jet stream. And so as the jet stream weakens, that steering gets weaker. And the idea is that those weather systems would tend to, stay over a given region for longer periods of time. And when that happens, that can lead to weather and climate extremes, right? Because you have like a storm system that's parked over, for example, a storm system that's parked over a particular region for a longer period of time. And, it leads to, maybe it leads to flash flooding, for example. So that's one potential implication of a weaker jet stream. There's also the idea that a weaker jet stream could potentially be a wobblier jet stream. So there will be greater north-south meanders of the jet stream. And, these north-south meanders also tend to be associated with extreme weather, right? Because if we have a ridge in the jet stream, as shown here on the lower right, that brings up warm air from the south. And, potentially these types of, of scenarios are associated with heat waves, very frequently. On the other side, if we have a dip in the jet stream, that brings cold air from the north south, and that can lead to cold extremes at mid latitudes. So, this is an idea that's relatively new in the climate literature. It's only really the last 10 years where this has really been, discussed. And I'll say that it's also still a very controversial idea. There are some studies that indicate that there is observational evidence for an effect of Arctic warming and sea ice loss on weather extremes at mid latitudes, leading to more weather extremes at mid latitudes. But there are also other studies that suggest that there's no such indication of any of these effects. So this is a very controversial idea still in the climate community, but it's potentially very important if it was to turn out to be a real thing.
Nobody else does their video, so I'm gonna stop my video. No.
Okay, so I wanted to maybe start to wrap up on a more, maybe a little more optimistic note, because I think much of what I've said, or maybe all of what I've said in terms of why does Arctic amplification matter, these are really negative impacts, right? I mean, we sea level rise and more extreme weather. But there are potential opportunities as well that may arise from the enhanced warming of the Arctic. And this is one example of that. This is just a title and abstract from a paper that was published a few years back that investigated what are the impacts of Arctic sea ice loss on 21st century transarctic shipping routes. And, the idea here is that as you melt sea ice and as the open water season over the Arctic Ocean lengthens, that will first of all, that will open shorter trade routes across the Arctic Ocean. It also will lead to, and those shorter trade routes will become more and more feasible for a greater portion of the year as the Arctic becomes increasingly ice-free. And you can see here in the abstract here some of the conclusions from this study that I'll just highlight a couple of the results. So it's stated that a sea ice ship speed relationship is used to show that European routes to Asia typically become 10 days faster via the Arctic than alternative routes by mid-century, and 13 days faster by the end of the century, while North American routes become 4 days faster. It further goes on to conclude at the end here that moderately ice-strengthened vessels will likely enable Arctic transits for nearly the entire year by the end of the century. So, in other words, if your ship is able to deal with some sea ice, the ice has melted back enough by the end of the century that you can potentially have trade routes happening across the Arctic Ocean throughout almost the entire course of the year. So there's potentially some significant global economic implications, potentially global economic benefit from these increased opportunities for trade routes across the Arctic Ocean. So maybe not all impacts of Arctic amplification are negative, but I would say that it's fair to say that in the sum, the impacts, the negative impacts probably outweigh the positive impacts. Finally, just a summary. Arctic amplification, again, as I've said a couple times already, is really a very, very prominent feature of climate change. We see it, we have evidence for it in past climate changes. We see it very clearly in our observations of recent climate change, and climate models very robustly project that Arctic amplification will continue into the future as we continue to increase greenhouse gases in the atmosphere. Why does Arctic amplification happen? Well, it's sea ice loss plays a huge role, as I've tried to convince you. And that's both because of the albedo effects of sea ice. When you melt sea ice, you expose a darker surface and you absorb more sunlight. And it's also because of the great insulating capability of sea ice. And when you melt sea ice, the heat transfer from the ocean to the much colder atmosphere over the Arctic increases dramatically. Also, as I said, a big part of why Arctic amplification happens is because of the temperature profile of the Arctic atmosphere. This near surface inversion that tends to inhibit vertical mixing and keeps heating confined near the surface. Finally, as I said, these are probably the two biggest reasons why Arctic amplification happens: sea ice loss and the strong stability of the Arctic lower atmosphere. But there have been a number of other factors that have been proposed, as I said, that would potentially also contribute to Arctic amplification. I showed you the example of increased poleward moisture transport and how that may contribute as well to Arctic amplification. I'll say that there are a number of other factors besides the ones that I've mentioned today that have been put forth that could potentially contribute to Arctic amplification as well. But these other factors are, I'll say, are just more uncertain. There's different studies have come to different conclusions about their importance, and so they're not as well established as the mechanisms that I've chosen to highlight here. Finally, enhanced Arctic warming and sea ice loss has had and will continue to have a number of important impacts on a range of human and natural systems. And this is not just limited to the Arctic. Hopefully the examples I've shown you today really, give you let you know that this is really a global problem. It's a global, Arctic amplification is a global scale phenomenon. The impacts, what happens in the Arctic, the enhanced warming and the sea ice loss impact the climate and therefore impact, these human and natural systems, far removed from the Arctic. So it's really a global issue. And with that, I think I will, that is all I have. And so I will stop, and I'm happy to take any questions that anyone has.
Okay, everyone, you can unmute. Everyone can unmute themselves now. And if you have questions, please throw them out. Richard.
Yes. Do you see an ice-free Arctic in the near future, or can make a prediction when it might be?
Yeah, I mean, it depends on what you mean by ice-free Arctic. There's
the Northwest Passage, making it a viable route
at certain times of year. I think that's potentially in the not too distant future. So what's focused on most often is the September sea ice in the Arctic, because that's the time of year when the sea ice reaches its minimum in the course of the seasonal cycle. And so there's projection, in terms of when the Arctic becomes ice-free in September at that time of year. The projections across the different models vary quite a bit. Some of them say that it could happen in the next, couple decades potentially,
Yes.
whereas others, hold that off longer, so maybe the end of the century. So in terms of, summertime sea ice, virtually disappearing, that could potentially be in the not too distant future. In terms of all sea ice disappearing completely from the Arctic, it's going to be, that's not something that's, if that ever happens, which I hope that we never reach that point, but if that ever happens, that's much more further into the future, even beyond 2100. We're not going to lose sea ice in the wintertime, even by the end of the century.
Oh,
I mean, there'll be some retreat of it, but we won't lose it entirely by the end of the century.
do you see the same model taking place in Antarctic? Because it's not water, it's land, right? There's different dynamics going on there.
Right. Yeah. And that's a great
Yes, right.
point. The Antarctic has been behaving very, very differently over the last few decades than the Arctic has. We've had, as I've talked about all this morning, we've had Arctic amplification, we've had polar amplification in the Arctic region, but we really have not had it yet in the Antarctic region. There's the expectation that will change, both based on physical understanding and also based on climate model results, but it hasn't happened yet. And it's really not completely understood why that is. There's different theories that are out there. One idea is that the Southern Ocean that surrounds Antarctica is very important in drawing down heat from the atmosphere, and that heat gets mixed at to great depths in the Southern Ocean. So it's likely that the Southern Ocean has been important in slowing down the warming over the Antarctic. But there have been other theories that have been put forth, about why the Antarctic has not been warming like the Arctic has, and one of those is just there's a whole lot of climate noise in the system, just climate variability that's not related to increasing greenhouse gases. And so there's some suggestion that what we've been seeing in the Antarctic over the last few decades is there's been a lot of climate noise, so-called internal variability that's been slowing down the warming in that region. But I'll just say to add to that our records of Antarctic sea ice extent. For much of the past several decades, the Antarctic sea ice the trends have been pretty flat. If anything, there's actually been, for much of the past few decades, a very small increase in the total Antarctic sea ice extent, which has been a bit of a puzzle again in the community, because when the rest of the world is warming, why has Antarctic sea ice not been melting? And I'll just say, though, the last few years, literally the last few years, like the last 2 or 3 years, there's some indication that that's finally changing. The Antarctic sea ice in the past few years has finally been below average, below the long-term average. And so, is this a sign that things are finally starting to change over the Antarctic? Well, we have to wait longer to see whether that's the case. But there's the expectation that things will start to eventually change over the Antarctic. But as you said, yes, the dynamics are very different. Because the Antarctic is a continent, at the pole and ice sheet, and the Arctic is ocean. So that makes the dynamics very different. The Antarctic is also surrounded by a circumpolar ocean, the Southern Ocean, that, as I said, is very important for drawing down heat, which is not the case in the Arctic, given the presence of land masses. So the dynamics are very different. So that partly explains why the climate changes over the last few decades have been very different.
Right. Thank you.
Has a study been done on greenhouse gases for the northern versus the southern hemisphere?
Do you mean in terms of the?
Well, I'm thinking in terms of the population density is more in the northern hemisphere, so we tend to pump more of the greenhouse gases in.
Right. So yes.
Although some of the southern countries are doing burning their forests so they can do.
Right. So yes, certainly you're right that, but the overwhelming majority of the greenhouse gases that have been put into the atmosphere have been from the northern hemisphere. But in some sense, if we're interested in what is the climate response to that doesn't really matter, because the main greenhouse gases are well mixed in the atmosphere, CO2 and methane. So even though they're being emitted mainly from the northern hemisphere, they have a very long lifetime in the atmosphere, so they have the chance to be transported across the globe. And so the effects, there's going to be climate effects even far removed from where the sources of those greenhouse gases are. But you're right that the Northern Hemisphere has really been overwhelmingly the main contributor.
Michael, one of the questions that came to me as you were talking is that with the retreat of the sea ice due to Arctic amplification, there may be opportunities for changes in where naval fleets are based.
Mm-hmm.
And we can see a lot more in the way of US and Russian and Canadian navies in the Arctic.
Yes, definitely. I mean, and I think, you know, for that reason, the Navy has a huge interest in the Arctic and what's happening in the Arctic. I don't know a tremendous amount about that, but I certainly agree with you that there's potential. You know, I focused on in that last slide on just, you know, the global economic impacts of increased Arctic trade routes, but I mean, there's other impacts besides, you know, there's impacts on military, you know, operations and so forth as well, which of course is tied into the economic impacts. But
we heard a little bit about some of the local economic impacts last month and at other times with Chris Zappa's work.
Okay,
In Katsugu. So it sounds like the native hunters are going to have harder time getting to their traditional hunting grounds.
yes, and that's one that, you know, that's one impact that I did not mention in my talk today. Yeah, I mean that the loss of snow and ice, you know, and the enhanced warming. I mean that's going to affect, you know, significantly the way of life of native people in the Arctic. I mean, you know, as you said, like they're the traditional, you know, methods of gathering food, you know, hunting and traditional methods of food preservation, you know, that rely on having cold temperatures and, you know, things like this are you know, so a huge number of impacts on just the local communities in the Arctic. And yeah, like you said, Chris has been doing some work, you know, in that area, you know, bringing in some native peoples, you know, into his research, which is, I think, is great.
Okay, other questions? I know a number of you are not shy about asking questions, so please jump in. Richard, you up again?
I'm here. No, it was it. Thank you.
Okay. So I'm going to have this recording posted eventually by my colleague, Christiana. And when it's up, I'll send a message out to everyone
Thank you.
that it's available. I apologize for some confusion over the starting time, but some of you missed part of the talk. But I think I've got all the names of who's been here. And we'll let you know when the full recording is up, so you can catch the part you may have missed.
Well, I did not show up at 11, so that was a good thing, right?
Good.
Yeah,
I knew I
that
was going to get,
would have been interesting.
well, I would have just had a longer introduction.
Very long introduction, right?
Oh, yeah. Okay, so the next Earth to class is towards the end of April. We'll let everybody know. We're going to be away from the Arctic theme that we've been at for the past few months and dealing with some tree ring studies. And we have 2 more Earth to class in this series. And then at this point, we are planning to continue Earth to class into the future. Although, as some people will tell you, that I'm getting to the point where, having been born in the Ordovician, it's getting harder and harder. I realize there's a few of you who are even older than I am, but none of us are ready to stop at this point. So we'll keep doing this. Thank you all very much. I'll be sending out certificates a little bit later. Michael, thank you for a very interesting and informative presentation.
Well, thank you again for the invitation to participate today, Mike, and thanks to everyone who joined again.
Thank you.
Thank
Just
you,
to
Michael.
explain how these things come about, we had some kind of a social event at Lamont. What was it, back in the fall?
I think it was probably the summertime. I think it was an ice cream social, if I remember correctly.
Yes. So I wander around with my ice cream and invite people to give talks. And we appreciate Michael willing to take his time and join us. Okay, I'm going to stop the recording again.